Right, this is quite a big example, and it can be a little bit tricky, although it is quite a useful technique when you're needing to sketch or interpret a sum or difference of two different trig functions. Being able to state them as a single function can be very useful. A good idea to have your calculator with you so that you can in fact confirm to yourself that you have produced an equivalent function. All right, let's have a look here. Let f of x be 2 sine of x minus 2 root 3 cos of x. And we need to express this in the form r sine x minus alpha. So notice I've got a sine and a cos, and I need to express it as something, or sine times sine of x minus alpha. Okay. I can have a look on my formula sheet at my various identities. And if I look here, I've got a sine of x minus alpha. Well, I've got an identity for sine of a minus b. So maybe I can use that to help me to rewrite my sum, my difference of two different trig functions. So let's try that. So using sine of a minus b is equal to sine a cos b minus cos a sine b. Okay. I need to let this thing that I've been given equal what I'm looking for. So let's do that. Let 2 sine of x minus 2 root 3 cos x equal r sine of x minus alpha. So we're creating an equivalent expression. So I'm going to use my identity, and I'm going to try and see whether I can find or equate coefficients to be able to find a single value. I know that sounds a little bit weird, but bear with me, okay? If I have, in this case, if I make sine a minus b be my x minus alpha, so then it will become sine x alpha cos x sine alpha. That's where I'm getting these values from, because now what I'm going to say is, so 2 sine of x minus 2 root 3 cos of x is equal to r times, now the sine of x minus alpha, I'm using my sine of a minus b, so sine of x cos of alpha minus cos of x sine of alpha. All right. I can multiply my r in. So 2 sine of x minus 2 root 3 cos of x is r sine of x cos of alpha minus cos of x sine of alpha. All right. Now, I want you to notice something interesting, okay? And bear with me here. On the left-hand side, I have a sine of x, and on the right-hand side, I have a sine of x, and on the left-hand side, I have a cos of x, and on the right-hand side, I have a cos of x. If I just rearrange things a little bit differently, I can have 2 sine of x minus 2 root 3 cos of x is equal to r, actually I'm going to put this in a different color, r cos of alpha times sine of x. And maybe I want to put this 2 in that same color. So 2 sine of x, r cos of alpha sine of x, minus, and I'm going to have a different color, maybe red, sine of alpha, and maybe I want to put this negative 2 root 3 cos of x. So notice that I have a variable sine of x on each side and a variable cos of x on each side. And I can equate my coefficients. So 2 must be equal to r cos alpha, and negative 2 root 3 must be equal to negative sine of alpha. Okay, this is where we're going with this. So we're going to equate coefficients of our variables. Now, our variables don't look like our normal variables that we're used to dealing with. Our variables are actually a whole trig function, sine of x or cos of x, okay, of sine of x and cos of x. So therefore, 2 is equal to r cos alpha, and that's going to be equation 1, and negative 2 root 3 is equal to, oh, I've lost my r. Sorry, there's an r in here. I didn't expand correctly. There's an r in there. Is equal to negative r sine of alpha. Okay, and negatives on both sides. 2 root 3 is r sine of alpha. And that's my second equation. Now, these are looking a little bit more like things we recognize. So how about if we divide the one by the other, we could get rid of our r and then we can just solve for alpha. So 2 divided by 1, we would have 2 root 3 over 2 is r sine of alpha over r cos of alpha. And I've chosen 2 divided by 1 so that I get a sine over a cos, which I can deal with as a tan. So my r's are going to cancel, my 2's are going to cancel, and what I end up with is root 3 is equal to tan of alpha. And from methods, we know that tan is positive in quadrant 1 and in quadrant 3. Okay, so tan is positive in quadrant 1 and quadrant 3. And my base angle for a root 3 of tan is going to be pi on 3, root 3, 1 and 2. My base angle is pi on 3. Okay, so therefore alpha is going to be pi on 3. All right. Let's have a look. We now want to substitute alpha equals pi on 3 into 1. So we're going to substitute our alpha equals pi on 3 into equation 1. Just to mention why I didn't choose my quadrant 3 answer. I'm looking from equation 1 and equation 2, both sine and cos are positive. So you might want to say there, both sine and cos are positive in equation 1 and 2. Therefore, I'm looking for my quadrant 1 solution. Okay, pi on 3 into 1. So 2 is r cos of pi on 3. and cos of pi on 3 is a half, so 2 is equal to r times a half, and I can solve for r. So this is pretty cool because 2 sine of x minus 2 root 3 cos of x is actually equivalent to the function 4 sine of x minus pi on 3. Now pause this video, type it into your calculator, make sure you're in radian mode, but prove to yourself that those two functions are exactly the same function. All right. Next part of this is we need to sketch it. Now, I don't know how to sketch 2 sine of x minus 2 root 3 cos of x. However, I do know how to sketch 4 sine of x minus pi on 3. And that's what we're going to do. So, y is 4 sine of x minus pi on 3. And you've done this in methods, so in the form y is a sine of b x minus h plus k. Your amplitude is going to be 4. Period's going to be 2 pi over b, so your period is 2 pi. Means that our x-axis in divisions will be pi on 2. However, we have a phase shift of pi on 3 to the right. So my new x-axis divisions are going to be the lowest common denominator of pi on 2 and pi on 3. So I want to have pi on 6 as my x-axis divisions. If this is all feeling a little bit foreign, go back to your methods and make sure you understand that. Your mean position is going to be at y equals 0, and that means that the range of my function is from -4 to +4, and we know that our domain is from 0 to 2 pi. All right. Because of my shift, I need to know what my endpoints of my domain are. So I'm interested when x equals 0, I'm going to have y will be 4 sine of -pi on 3, and negative pi on 3 is in quadrant 4, sine is negative in quadrant 4, so y will be -4 of sine pi on 3, and sine pi on 3 is root 3 on 2, so -4 root 3 on 2, and that becomes -2 root 3. So my beginning of my domain is at 0, -2 root 3, and because I'm sketching one whole period, I can say similarly, when x is 2 pi, y is also -2 root 3. All right, let's sketch this. I always first sketch in a dotted line the y equals 4 sine x. A sine curve begins at 0. It's going to end back at 0. It's a positive one, so it will reach its maximum at pi on 2. It will cross my axis at pi, and it will reach its minimum at 3 pi on 2. So this is my unshifted function. And then I'm going to shift every single point pi on 3 to the right. So I've got divisions of pi on 6, so I'm going to move this point there. That point goes to there. That point goes to there. That point goes to there. And I know that I have a starting point at 0, -2 root 3, which is around about over there. And it's going to end at the same point at 2 pi -2 root 3. All right, so here is my function. Try and keep it nice and smooth. All right. This is y equals 2 sine of x minus 2 root 3 cos of x. All right. Now, they want us to solve for f of x equals 2. If we're using the equivalent function, it's a whole lot easier than if we're using the original one. So for f of x equals 2, well, we're looking for 4 sine of x minus pi on 3 equals 2. And that's where sine of x minus pi on 3 is equal to 1/2. And sine is positive in quadrant 1 and quadrant 2. And my base angle is going to be pi on 6. So therefore, my angle x minus pi on 3 must be equal to pi on 6, or x minus pi on 3 will be pi minus pi on 6. So x will be pi on 6 plus pi on 3, which becomes 3 pi on 6, which is pi on 2, or x will be 5 pi on 6 plus pi on 3, and that becomes 7 pi on 6, is it? 5 pi on 6 plus 2 pi on 6, 7 pi on 6. So my solution, where my function is equal to 2, will be at pi on 2 and 7 pi on 6. And if I have a look at my graph, that works pretty nicely, because over there, pi on 2 and 2 and 7 pi on 6. So 7 pi on 6 and 2.